So, welcome everybody. Today's talk is by Carla Cederbaum from the University of Tübingen, and she will talk on CMC-foliations of asymptotically flat manifolds. Please go ahead.
Thanks to the organizers for inviting me, and please interrupt me at any time with a question. I'm not sure I'll be able to follow the chat while I'm speaking, so please just, if Armin maybe could follow the chat in case a question arises from someone, but you could also just turn on your sound and speak up when you have a question. So let me just jump right into matters. So let me just review a very, I'm not going to say very old, but a very important result from 1996 by Huisken and Yau, which started the business of CMC-foliations. And they looked at the following setup. They had a three-dimensional Riemannian manifold, and they assumed that this is asymptotically Schwarzschildian, which I'll denote by AS. And they assume that this is asymptotically Schwarzschildian of order 4, and I'll say in a second what this means. So it means that M3 can be written as a compact set in a disjoint sum, in a disjoint union with what is called an end E3, and that being an end meaning that you're diffeomorphic to the exterior of a ball, of a closed ball in R3, and this diffeomorphism is going to be called phi. That's the diffeomorphism. And then, of course, this diffeomorphism gives you coordinates on M3 outside the compact set. And in these coordinates, we require that the components Gij look like 1 plus m over 2r to the power 4 delta ij. This is the well-known so-called Schwarzschild metric. That most of you will probably have seen at some point in your geometric analysis careers. And then you can deviate from this by a term of the order 1 on r squared. And I'll put a little 4 here as well. It's the same 4, it's the same number 4, which is here and here. And this little 4 there means that you can take a derivative of this asymptotic equation 4 times and differentiate all the terms on both on the left-hand side and the Schwarzschild term, and also the term in the bracket of the O. So the first derivative will decay like 1 over r cubed, the second like 1 over r to the 4, and so on. And you can do this up to at least 4 derivatives. So this is this assumption of the Riemannian manifold being asymptotic to Schwarzschild at order 4. And here this number m is a real parameter called the mass. And if you're familiar with the concept of an ADM mass, then if you computed the ADM mass of a metric of this form, then you would get this to be m as well. So this is the ADM mass of the metric G in a mathematician's language. And however, if we have any physicists or mathematical relativists among us, then I should be more precise and should not say that this equals the ADM mass, but instead should say that this equals what is called the ADM energy of G. And I'll say more about this later. I just wanted to mention it for the people who know what I'm talking about already. So under this assumption that the manifold is asymptotic to Schwarzschild with including at least 4 derivatives, then the theorem by Huisken and Yau says the following. So suppose M3D is AS4, asymptotic to Schwarzschild at order 4, then there exists a unique foliation by what is called CMC surfaces, where CMC stands for constant mean curvature. Now, they don't only prove existence and uniqueness of this foliation, they also prove a massive amount of extremely strong quantitative intrinsic and extrinsic roundness estimates on the leaves of this foliation. So plus quantitative, and I'm not going to be precise about those. Quantitative, intrinsic, and extrinsic roundness estimates. Okay, so let me make a sketch of the situation. So we will have our asymptotically flat manifold here. Maybe it has some interior, maybe there's some matter, maybe there's some topology. I don't care at all. I'm just going to study the whole thing outside some compact interior. So I'm going to look only at this end E3 that is introduced in the definition of asymptotic Schwarzschildianness. And then in this exterior region, in the end, I will have a foliation by lots of surfaces which have constant mean curvature, each of them. Draw one to the interior as well. And these surfaces, after the roundness estimates, turn out all to be spheres. And all these spheres have constant mean curvature, and the mean curvature parameter goes to 0 as we go out to infinity. So the mean curvature, goes to 0 from above as radius in these coordinates that I introduced goes to infinity along the foliation. One example that you should, of course, keep in mind is if you look at this formula for the metric being asymptotically flat, this formula here, then if you just have 0 error term at all, so if you just have this Schwarzschild metric, then the mean curvature, these constant mean curvature spheres are just the concentric spheres in this spherically symmetric Schwarzschild example. And you can explicitly compute their mean curvature in terms of the radial coordinate r of each of these round spheres, which are centered around the origin, and the mass parameter m from the corresponding Schwarzschild spacetime value.
Carla, there's a question.
Yes.
By Julian. Is that really just a perturbation of the trivial Euclidean picture?
Yes, it is really a perturbation of the trivial Euclidean picture outside the compact set. Of course, in the interior, you can have whatever you want. And it's not even just perturbed Euclidean space, it's perturbed Schwarzschild, which means that you have explicit control, as you see in this formula with the many arrows now. You have explicit control up to order 1 on r squared even. Yeah? So from the metric perspective, you're almost Euclidean space, but you even understand exactly what happens at the 1 over r power. And then there's even a gap up to the 1 over r squared power. And this includes for derivative. On the metric of on the level of the manifold, then outside the compact set, you just R3 minus the ball. And I should actually put a little plus or 0 here. And then in the theorem, I should say with positive mass.
So there's another question in the chat.
Yes.
Could one consider more than one ends?
Yes, so you can, the result that Huisken and Yau prove is really a result about an asymptotically Schwarzschildian end, because you only prove existence and uniqueness and roundness estimates on the foliation in one of the ends. So if you had other ends, as long as they also have this strong decay to the Schwarzschild metric in this AS4 class and have a positive mass, this can be done separately for each end. So the interior of the manifold can even be empty. It doesn't matter at all. And so this is a pure statement about the end. And of course, in the statement of the existence of the foliation, you even don't have maybe the end you started with, but maybe in a smaller end. So an end of the original end. So it's really a statement local to the end, near infinity.
Yeah.
there a follow-up question?
Not yet. Looks okay.
Not yet. Okay. So in the trivial Schwarzschild example, you have these concentric spheres, and here what it shows is that if the metric approaches the Schwarzschild metric, then you still have a surviving CMC-foliation. They're not going to be round, but they're going to be more and more round, both intrinsically speaking in terms of the Gauss curvature, and also extrinsically speaking in terms of the second fundamental form becoming very round as you go out to infinity. So by now, today, we have very many generalizations of this theorem. And I'm not going to be able to mention a complete list of people who contributed to this. And all the mention I will make are going to be in alphabetical and not chronological order, because people alternated also. So I'm just going to simplify the picture very much. So the one generalization is to weaker decay assumptions. So not asymptotic to Schwarzschild, but just asymptotically flat in a certain sense, and I'll be more precise about this later. Still asymptotically flat. And in this direction, people who did the most amount of work are Lamm, Huang, Yang, Metzger, Christopher Nerz, and Ye, but there's also work by many other people. Another direction of generalization is to modify the asymptotic picture entirely and go to completely different asymptotic conditions. And one problem people have considered is to look at asymptotically hyperbolic manifolds. The names here are, again, Christopher Nerz and Neves and Tian. And I'm not sure if there are others, but I'll put dots as well. Then other sets of asymptotic conditions that have been considered are asymptotically conical manifolds by Chodosh and Eichmeier. And then there are also other types of asymptotic conditions that have been considered. And another direction of generalization still is to look at different foliations, which is the direction we will go in this talk. And here, before I talk about my own work, I would like to mention the foliations by constraint Willmore surfaces. By Eichmeier and Metzger. Sorry, that's not true. By Lamm, Metzger, and Schulze. And also foliations of ends in the setting of GR and general relativity. I will say about this more later. And here, what I want to mention is a foliation by what is called constant expansion. Constant expansion, or equivalently, in a more Lorentzian language, constant null mean curvature. Foliations. And these have been considered first by Jan Metzger, and then later by Christopher Nerz, and I'll briefly mention them again later. And another one I would like to mention is the so-called STCMC-foliation that I'll talk about today by myself and Anna Sakovich. And here, CMC is constant mean curvature as before, and ST stands for space-time. Of course, I'm going to say more about this later. Another direction of generalization of the Huisken and Yau result is in the direction of higher dimensions. And this is where I wanted to mention Eichmeier and Metzger. A nice generalization to higher dimensions. And I should mention that my collaborator Melanie Graf and I are in the process of generalizing also the STCMC result that I'll talk about now to higher dimensions. Okay. So these are all the directions of generalizations that I know about that have been studied as a result of the big impact that the Huisken and Yau work had. And one more thing I would like to mention is that the result by Huisken and Yau goes back to a question asked by Christodoulou about the center of mass in general relativity. And I will come back to that original question by Christodoulou at the end of the talk, if the time works out, depending on the amount of questions we have. So now let's go. Question. Is there another one?
Yes. Does higher dimensions mean above or below 8?
Say again, please.
Does higher dimensions mean above or below 8?
I don't think 8 is a threshold there. I think it's generic. Because the method doesn't use any of the positive mass theorem methods that you would like to.
So the follow-up is there are no problems with area minimizing singularities?
I don't think so. I would have to study it more carefully. I haven't looked at it in a long time, but I don't think so because it works as a more perturbative result from the round spheres you already have in Schwarzschild. But I'm not an expert on the higher dimensional case yet. So I hope I'll be able to answer this in a couple of months. Any more questions?
No, it doesn't seem like it.
Okay, thanks. So let's move to what is called the initial data setting in general relativity. And this is the stage for the STCMC-foliation. And if you're not at all interested in general relativity, please bear with me anyway, because one of the messages coming from the study of this STCMC-foliation in the context of initial data sets of general relativity will be an understanding of a problem of a coordinate representation of the CMC-foliation in just Riemannian geometry, which I'll mention this problem later and also why it's resolved or in what sense it is partially resolved by the STCMC-foliation. So here the setup is pretty similar to what we've looked at before, just the decay is much weaker. So we have a Riemannian three-dimensional manifold. And we have on top of this Riemannian manifold, we have another piece of data, which is a symmetric 0-2 tensor field on M, and it's symmetric. And if you know about general relativity, you should imagine it as the second fundamental form of the initial data set in the space-time. That's why it's a symmetric 0-2 tensor. But it doesn't really matter for what I'm going to talk about, what it is. You can do everything completely abstractly without any reference to space-time. And we're assuming the following asymptotics. We're assuming that there's some epsilon bigger than 0 and some entire number k, which is bigger or equal to 2. So maybe I should have written it as a natural number anyway. And then M3, again, as before, is split into a compact set in a disjoint union with an end E3, which is again diffeomorphic to R3 minus above. And this diffeomorphism gives me again coordinates xi and a coordinate radius r. So just to be clear what r is, it's what you would think it is. And then the metric components in these coordinates should look like now not the Schwarzschild metric, but just the Euclidean metric, plus terms of the order O of r to the power -1/2 minus epsilon. And there's a little k down here indicating the same process as I illustrated with the number 4 in the Huisken and Yau assumptions. Here now it can be any number k larger or equal to 2. And the decay is also much less strong. So the Schwarzschild metric had its mass term at the order 1/r. And if epsilon is small, this is even before the order of r. So we only prescribe the 0th order term, and then the deviation from this 0th order term is at the order -1/2 minus epsilon. And I can say more if people are interested later of why this is a good assumption. And the components of the tensor k in the same coordinates of the form O k minus 1 r to the -3/2 minus epsilon. So this is one part of the assumption, which the metric part looks familiar and much weaker, of course, than the assumption I presented before. So this is called asymptotically Euclidean here because we are asymptotic to the Euclidean metric. And now we have this additional tensor k flying around, and we assume some decay on it as well, which is a faster decay than the correction term here in the metric by 1 order. And then as a compensation of that, there's 1 order fewer derivatives on which we're imposing this decay. But we have an additional assumption, or rather a pair, and this is like this, the scalar curvature of the metric G minus the length squared of the tensor K plus the trace squared of this tensor K should decay like OK minus 2 r minus 3 minus epsilon, and I'll say something about this in a second. And the other condition is that the divergence with respect to the metric G of K minus trace G K times G should have the same decay. Instead of this, you could also ask for this to be in L1 on R3, or on the end rather, on the exterior of the ball in R3. Okay, so let me say a few words about this. The conditions in the O, of course, in the statement of our theorems will take the form of weighted Sobolev spaces, and the O notation here is a more accessible version of these weighted Sobolev spaces I'm choosing for the presentation, not in the proof and not in the statement of the theorem either. And if you are familiar with the concept of ADM mass in just Riemannian geometry, and you can just ignore the K in all of this, and then the first one of these 2 last equations, this one with the orange arrow, becomes an integrability condition on the scalar curvature. So if you're familiar with the work, say, by Robert Bartnik or by Piotr Kruschel on well-definedness of the ADM mass, then you will be familiar with the condition that the scalar curvature should be in L1. And this pair of conditions here, of these 2 expressions being in L1 is the general relativistic initial data set generalization of this condition that you need to get what is called the ADM energy and the ADM linear momentum, and as a consequence, the ADM mass to be well defined. So this is a setting where we know that in the setting, the ADM energy, the ADM linear momentum, and as a consequence, the ADM mass, which arises from these 2 is energy squared minus P squared. They are all well defined in this setting. And it turns out if you pick epsilon equals 0 in these assumptions, even just in one of the assumptions on the metric, or on the second fundamental form, if you put epsilon equals 0 there, then you will find examples in this category of decay where the ADM energy or linear momentum and mass are not well defined. So you need positive epsilon in all the above assumptions in order for this to be really well defined. So this is why we need this epsilon there. And it's also the reason why there is this 1/2 here and the 3/2 here. If you put lower decay, as I just explained, you don't get well-defined energy and linear momentum. And the 3 here, of course, is the dimensional restriction on the L1 integrability. So I'm not going to write the formula for the ADM energy and linear momentum or any of that. And I hope you're either familiar with it or you will ask me if you need to understand it at some point of my talk. So here's our theorem. So if we have a system M3GK of the above decay, and EADM of this metric is non-zero, then what we can prove is then we have, oops, sorry, then we have a unique foliation by these STCMC surfaces in the end, in the asymptotic end, plus quantitative intrinsic and extrinsic roundness estimates, which were of course much weaker than the estimates that Huisken and Yau get, because we assume much less decay than they do. But they have the same quantitative quality as the estimates have in the CMC foliation case if you assume the same decay for the metric and the scalar curvature in the CMC foliation case. And what is this mysterious STCMC condition? So a surface sigma in M3 is called STCMC if, and now I'll write a number of different ways to write it down, if something we call curly H, and define as the mean curvature squared minus the trace over the two surface of K squared is constant. Another way of writing this is to call this H squared minus P squared, where confusingly this P is a name given to this two-dimensional trace of the second fundamental form. This and this is the same. It's just a different name for the same thing, and it has nothing to do really with linear momentum. It's just something that's also carrying the name P, typically in our literature. And you can also, of course, write this as the square root of H plus P times H minus P, not surprisingly. And then you can also write this, for those of you who know some Lorentzian geometry, as the product theta plus times theta minus, which again is the same thing, just written in different letters. So this would be the null expansions mentioned briefly before, but I don't expect you to know what they are for what follows. So here is a geometric interpretation of what this means. If you think of your manifold, which is the initial data set M3G with its second fundamental form, as sitting inside a spacetime, and then you consider the two surface in this initial data set, so in this Riemannian manifold, then of course this surface has a codimension 2 mean curvature vector. And as a codimension 2 mean curvature vector, you can split this vector into the normal part and the tangential part to this three-dimensional surface, and then the tangential part will be the codimension 1 mean curvature vector, and the part in the normal direction, so in sort of the time direction, normal to the surface, will correspond to this trace of K. So what we'll find is that the length of H in the Lorentzian spacetime setting will be nothing else but this same quantity we considered that before. And this is why we call it the spacetime mean curvature. And STCMC again means that this spacetime mean curvature is constant. So in particular, if you look at this condition, maybe in this form here, and you think of the case where you're just in a Riemannian manifold and this tensor K is 0, then curly H being constant is just the same thing as H being constant. So this is really a generalization of the CMC-foliation to this initial data setting, in the sense that if K is 0, then we recover this, the CMC-foliation. And also this curly H had been known before in the study of horizons and in initial data sets, but I'm not going to go in this direction unless someone is interested. And what I want to point out is that this condition on the non-vanishing of the energy here is the replacement of the positivity of the mass in the CMC-foliation result for Huisken and Yau. So this is a weak version of positive M. And another result that we get, so we get existence and uniqueness of this foliation. We get nice roundness estimates as you approach infinity in this foliation, but we also get that the leaves of the foliation are asymptotically Poincaré invariant or equivariant, asymptotically Poincaré equivariant. So the Poincaré group is the isometry group of Minkowski spacetime, and if you have an initial data set that has the decay that I described, it's a good indication that the spacetime in which this initial data set sits is asymptotic to the Minkowski spacetime in a pseudo sense. And then if you look at the leaves of our foliation as you go out to infinity and study, for example, how they transform under time translation in the asymptotic Minkowski spacetime, then you will find that each leaf of this foliation asymptotically behaves in the dominant term as you would expect from a point particle in the special relativity corresponding to the Minkowski spacetime. So let me just explain this for time translation in the sketch. So if I have the H equals H naught surface at some time t equals 0 in my spacetime, and then I consider the surface with the same numerical value for the spacetime mean curvature at some time delta t, then of course this surface looks a little bit different. So, and I'll get a little cylinder here of how it transforms in time. And then if I look at how it transformed in time, then I'll get the ddt of this H equals H0 surface will be like the ADM linear momentum divided by the ADM energy plus lower order terms. And lower order terms means along the foliation, either as you take the radius of the leaves out to infinity, or you take the mean curvature down to 0, which means the same thing in different letters. So if you're familiar with special relativity, this means that a point particle velocity can be computed as the ratio of the linear momentum over the energy of the point particle. So we get a number of properties of this type. And before I end, I would like to make the promised connection to the center of mass in general relativity and to this problem if you coordinatize the CMC-foliation. So let's start with the coordinatization. So if you have such an asymptotically flat end with CMC or STCMC or any other foliation of this type, and I'm drawing the leaves of the foliation here, now in a different way, then of course, because you're in this asymptotic end, you can take this diffeomorphism phi that takes everything to R3 outside some ball, which I'm not going to draw, and then you can just push these surfaces which have a certain geometric property in the Riemannian side. So I hope this is on the left-hand side for you. And you can just push them here. And you get their image under this diffeomorphism here. Of course, in Euclidean space, they will typically not have constant mean curvature, but they will still be legitimate, nice, almost round two spheres. So almost CMC, and more so in a quantitative way as you approach infinity. And then what you can do is for any of these surfaces, if you have one of these surfaces here, then here you have phi of sigma 2 here, but I'm just going to drop the phi from now on. What you can do is in Euclidean space, you can compute the average position with respect to the Euclidean metric on any of these surfaces and call this its coordinate center. So if we do this for all the surfaces in the foliation, I hope you can see the yellow well. For each of the surfaces in the foliation, you will get some point in Euclidean space, and typically these points will all be in the middle. So what we really get is, as we have a one parameter family of two spheres, we will really have also a one parameter family of these Euclidean centers as you parameterize by either the radius of the two spheres or their mean curvatures. Both are good parameterizations. And what Huisken and Yau claimed, so a claim in the Huisken and Yau paper from '96 that I described in the beginning, is that the limit of all these average positions, and I label the surfaces by their mean curvature now because they're now constant mean curvature spheres of this, as the mean curvature goes down to 0, could be called Z and would be a nice definition of center of mass of a Riemannian manifold. And this, I think, is what Christodoulou had in mind when he suggested to look at these CMC-foliations. The only problem is that this doesn't always converge, which is a joint result of mine with Christopher Netz from 2014. So there are examples, and actually they're pretty easy to write down, and I'll be happy to do so if someone asks later of the Riemannian manifolds, which are asymptotically flat to order 4, have positive mass. So they satisfy all the assumptions of the Huisken and Yau paper, but the limit above does not exist. And it turns out that if you, instead of picking the CMC-foliation in this picture here, if you pick the STCMC-foliation, then the examples that Christopher Netz and I constructed for this divergence miraculously get rectified and converge. So in these examples, this divergence stops if we use the STCMC-foliation. But I need to say that it stops in those examples that we had. And just as the last thing I want to explain, let me mention that there are examples, and I will explain one in a second, where really you can still diverge in this limit along the STCMC-foliations for reasons that are so elementary, and I hope you will share this view in a second, for reasons that are so elementary that they need to prevail and there cannot be a workaround except by choosing particularly nice coordinates, which is something which is work in progress by myself and Jan Metzger. To choose such coordinates, and I'll mention this again later. But so here, let me just sketch the example. So here's a problem. Here's a convergence issue that prevails, that keeps existing for the STCMC-foliation. And this is as follows. We take just the Riemannian Schwarzschild manifold and k equals 0, where this is just Schwarzschild. So the exact same example that was the leading term in the asymptotics in the Huisken and Yau example. So we know that this has a perfectly fine CMC foliation, which coincides with the STCMC-foliation and most other foliations that you can conceive that have any physical or Riemannian significance. And these leaves will be the centered spheres in this spherically symmetric spacetime. But now we choose new coordinates. On the spacetime, and the new coordinates we are going to choose are going to be yi, in the xi we had before, plus some ai, which is just a set of 3 real numbers. For each I, 1 real number, but not 0, or at least not all of them 0. And then we're going to multiply this by sine of ln of r. And of course, we're going to do this only near infinity, so you don't need to worry about this not being a nice coordinate transformation in the neighborhood of the 0, because we don't care about x equals 0. We care about very, very large absolute value of x, very, very large r, right? So this is a completely fine coordinate transformation on this completely fine Riemannian Schwarzschild manifold, on which we have our very fine existing and unique CMC-foliation, which coincides, I'll repeat, with the STCMC-foliation. And if we write the metric G in components with respect to these coordinates yi, it's still going to be asymptotically Euclidean in the sense I defined it, that is the assumption in my theorem with Anna Sakovich. Still going to be asymptotically Euclidean of order k for some epsilon bigger than 0. So same asymptotics as above. But it's not going to be asymptotically Schwarzschild anymore in those coordinates, because this translation multiplied by the sine ln r will break the spherical symmetry in the expansion of the metric. So the geometry, of course, stays spherically symmetric, but its coordinate representation at leading order term will still be delta ij. So yes, spherically symmetric, but at the order 1 over r, we will have a non-spherically symmetric term. So it's apparently not spherically symmetric, even though the underlying geometry is perfectly fine spherically symmetric, because we have chosen these coordinates yi, which break the spherical symmetry. And then if you compute now these, the phi y push forward of these mean curvature spheres, which are the same as this STCMC curvature spheres, and you take the average position vector of this y, in the same method that we did before. So we tried to find the center. If this was a round sphere, we would want to find the center, and it is a round sphere, but it doesn't appear to be a round sphere in these coordinates y. And then we try to take the limit as h goes down to 0 along the foliation of these average points. Then this diverges, and this diverges at a speed sine ln r times this vector a formed from the a1, a2, a3 in the coordinate transformation. Okay, so we have an example here of bad coordinates on a very nice manifold, which destroys this convergence of the coordinate centers. And of course, if we didn't have a spherically symmetric manifold to begin with, we couldn't really say if we had this divergence, if it was a problem with the coordinates or a problem with the manifold. And this is a project I have at the moment with Jan Metzger to try to write down good conditions on coordinates so that the coordinates will not be the one who destroy this convergence. But the examples I mentioned before here with Christopher Nerz are of a different nature, and there what happens is that really the manifolds, or rather the initial data sets, are the problem that causes this limit to not converge. in the CMC-foliation, and then this part of the problem is rectified by the STCMC-foliation. So I think I still have 2 or 3 minutes to say something about the idea of the proof. And the idea of the proof is to connect an initial data set M3GK by plugging in the little parameter tau here from 0, 1 to the Riemannian analog. So this connects this to M3G k = 0, where then in this Riemannian case where k is equals 0, this STCMC-foliation that we're looking for would be exactly the CMC-foliation. And it turns out that the result by Nertz I mentioned before, I think from 15, proves existence and uniqueness of the CMC-foliation in this k = 0 setting under exactly the same decay assumptions that we made. So Nertz gives us existence and uniqueness of the CMC-foliation in this setting. And then using this parameter tau, and as you might have guessed, an open and closed argument, using the stability operator of the STCMC condition, we can use the implicit function theorem and related methods to extend the CMC-foliation in this k = 0 setting to the setting where we actually have the k that we started with in the beginning. And this leads to a definition of a stability operator, of which you do an eigenvalue analysis of the asymptotic eigenvalues along the foliation, and a lot of estimates there. And all of this, as I said in the beginning, is done in weighted Sobolev spaces. So all the O notations you saw were just talk versions of Sobolev spaces. And at this point, maybe I thank you for your attention, and we're happy to answer more questions.
Thank you very much.